Hi there, and welcome to today's lesson for BCIT Technology Teacher Education 4044, our structures class. And in the last video, we talked a little bit about the truss challenge, laser cut truss challenge that we're going to be doing. And in our last lab, we cut out some small trusses to try and understand the forces that were acting on them and how our larger trusses were likely to fail when we went around and tested them. And this is part of the engineering design process. And the engineering design process is often drawn as a loop where you go around and you iterate and you test and then you come back. And there's a break between what I call tinkering and actual engineering. In tinkering, you just go out and you do something and you try it again. And if it doesn't work, you try it again. And basically, you're working with full scale models and you're working with the real life thing that you're going to be building. And that doesn't work so well in engineering. You know, it's hard to build a Mars probe and then say, let's test that and see, oh gosh, we just bashed $1 billion Mars probe into the planet. I mean, it's been done, but it gets expensive to do things that way. You know, when they built the Port Mann Bridge, you didn't really want them to go out there and say, well, we'll just try it like this and we'll see how many cars it can hold. And if it falls down, we'll just build a new one. That would be a bad approach. So what engineers will do as part of that design process is there will be a lot of prototyping and modeling and attempts to understand what's going on in the structure. So we started out by doing some calculations where we could understand the forces in a truss, and I'll go back and go over some of those calculations today. And then we talked a little bit about how we could take a look at column buckling and how the loads of a member in compression behave quite differently than when a member's in tension. And so that was a lab a couple weeks ago where we crushed on a column and we took a look at that and recorded some data for the hardboard that we're going to be making our truss out of. So we're starting to understand the materials. And in this lab, we went to understand the shapes and the structures and how these materials work when they're put together. And we came up with what I found to be some really interesting results. And in a moment, I'll tell you why they were so interesting. But well, the main thing was these structures were a lot stronger than our previous testing had indicated, which from an engineering context is a good thing. It's always better to come up with, something that stands up longer and withstands more load than what you predicted. You can live with that, but since we're also trying to optimize our weight, maybe we needed to understand the structures even better. So let's take a look at what happened and how this structure failed. And the first thing that happened was we're working with a truss that is 100 millimeters from here to directly down here. So right angle right in here, 100 millimeters, and a 200 millimeter length right along here. So we're working on that structure. And then we're applying a load right in here, and there's a pulley wheel right down in here. Originally, when I was testing this, I was just dangling a 10-pound weight off of here and found that that was too unstable. The weight kept swaying back and forth from side to side. And really what we were testing was how stable I could hold the weight. So we needed a better way to test this. And with the 10-pound weight, it was either stand up or fail. We didn't actually get an accurate reading of the failure point. So this rope right here comes down. You can see the top of a little pulley right here. Pulley's fairly low friction. Comes down this way. And at the other end, we have a fish scale, and you can pull on the fish scale. And then if you keep a close eye on your fish scale, then you can see at what point the entire structure collapses. And it's kind of neat because I had my camera on here, and you can see if you slow it down, right in there. Okay, we're just starting to go now. Look at that top right there as it comes over. It's coming out towards us. And there you can see the structure starting to go. And we've got a buckling failure in the long compressive member closest to us. So you can see it comes down and then it starts to pop out to the side or to the inside, just like this. And this part starts to come down here. now all of our structural integrity is lost and the entire structure comes apart like that and impressive failure. Now, the reason it was so good to have the video on it, why I think it's really important that you record, and if your phone has a high speed mode on its camera, try to get it at higher speed as well. Make sure you've got lots of nice light, is because the question is, where did it fail first? You can see that by the time this structure is lying on its side, the tensile members have snapped. Um, we've got a snap right here in this compressive member, but did it fail in tension or did it fail in compression? That makes a big difference to where we're going to go to strengthen our structure. And when we play it back in slow-mo, you can see right there that that was very clearly a buckling failure in that side. When that side buckled right in there, that kicked the bottom out right there, causing this to rotate a little bit in there, which probably put additional tensile strength on there. The bottoms were so slim that anything other than tension is going to cause them to fall apart. And there goes our structure. So when you're doing these tests, record as much data as you can because it's really interesting to see how they fail. Now, one of the things that I noticed from watching this was that this member right in here, now I don't have the best angle on it because I'm just looking at it from the side, but if you look at the shape right on here, the shape of this beam right here, or member, I should say, well, it's working a little bit as a beam. The shape of this member right here doesn't look exactly like the ones that we tested in the lab. So what do I mean by that? Well, let's come over here and oh, I'll talk about that later on. And right here, okay, you'll recall doing this test in the lab and look at the shape of that curve. That is a continuous smooth curve coming right up and down here. Okay, now that is indicative of our load conditions, and that's what I'd intended for this truss loading, is our simplest type of compressive failure, our simplest buckling failure, is when you have a pin at each end, and that's free to rotate at the ends right here, and you can see that it's free to rotate because this is not being held in place. But when we look at this structure right here, it doesn't look like that's free to rotate right around there. It looks like this is straight, restrained by this node, because this node is glued onto this piece of dowel that comes over here. And then it comes in, it goes straight for a little bit, and then it buckles out right here. And then it's restrained down at this end because this piece right in here hasn't flexed in or out either. So we've got slightly different loading conditions at the ends than we did on some of our tests. Now, this is something that I wanted to go and confirm. So I did a couple of tests one evening, and pardon the video is not really focused on what's going on here. I just cut out the long compressive section that failed, and instead of putting it up on the truss, I just lay it down, truss testing jig, I just lay it down right here, and you can see there's that purple rope pulling down on it. And you can see the mode of failure that happens right in here when we slow it down. It's being pulled in this way. And then as the pressure goes up, I think I'm around 9 kilos right there, 90 newtons of force causes that to pop off to the side. And sure enough, if you look right here, you can see those two pieces remain parallel to each other because of the glue holding them onto that piece of dowel. They can't flex from side to side, so they're not truly pinned in the direction of failure. They're actually fixed in the direction of failure, giving us more, I'll say an S shape, but it's not really an S, rather than that C shape that we saw when we were doing it with the compression testing jig. So our end conditions in the truss are a little bit different. Now, what was really interesting was that this mode right here failed at really close to 9 kilos, 90 newtons. I've got another one right in here of another mode of failure that comes along in here. Same sort of loading. And this one, you can see this one goes, instead of having both of them go together in parallel, this one goes right in here first. Now, why would it fail differently? Well, maybe I didn't glue it up quite as parallel. Maybe my hook is almost looks like it's slightly off to one side instead of being perfectly centered, so there might be slightly greater forces on this side in this test. Um, but actually, it held just about the same amount. I think we were at like 9.7, 9.8 because I was doing the test all by myself and just sort of jury rigging it. I didn't have my have the fish scale in the frame while I was doing this, so I don't have a perfect test on here. But you can see that one again. We've got a straight bit, and then we've got a C coming together in there. So two interesting different failure modes, um, both at very close to the same amount of load, and both quite a bit higher than we would have predicted if I just had a single piece pinned at each end right in here. My predicted strength for a single piece pinned at the end right in here was going to come in, I think, around 17 newtons or something like that. And now if you take the 80 or so newtons that we had coming down in here, 80, 90 newtons, it was somewhere in that range. Split that across the two members. Each one of these is supporting 45, almost twice as strong as what we predicted, and actually quite a bit stronger than in the tests that we saw right here, where this was also holding a lot more than 17. So anyways, interesting results and a little bit confusing right now. So let's go over here and go back to the beginning where we started talking about truss strengths, and let's do some calculations so that we can understand where these numbers that I'm throwing around came from. So when I originally was setting up this lab, I did some experiments and I came up with a fairly simple design for a truss. And like I say, I wanted it to hold a 10-pound weight. So there's 454 grams to the pound, so that's 4.54 kilos is the 10-pound weight. And so I just rounded that off and said, okay, I'm going to apply a load of 46 newtons at the top of the truss. Now, keep in mind, there's two sides to the truss. So each side of the truss, if we loaded it perfectly equally, would have to hold 23 newtons. That was the basis for my design. Okay, and now you can design whatever truss you want with whatever load you want. It's all good. Let me just adjust this camera right here. There we go. Okay, so now looking at this truss right here, if this has 23 newtons coming down this way, we need to be able to go through and solve the truss. And as I was talking with one of the students after the lab the other day, we are doing some advanced work and we are doing some basic work in here. So I should really specify what some of the basic stuff is and what some of the advanced stuff is so that you know that you're getting the core content from the course. You should be able to take a truss like this and calculate the reaction loads at each of the nodes and which members are in compression, which members are in tension, and the amount of compressive and tensile force in each of the members. This is a pretty simple one, similar to something that we did a while back. And remember that it's going to start out by balancing the moments. So really, we've got something similar to this right here, where our force comes down at a distance of 100. We've got 23 newtons right there. And we've got a force acting up right there. And we're going to say this is pinned or fixed right here. So we've got a lever arm that could swing back and forth like that. And what we need to do is say what force is acting up right in there. Well, if I've got 23 newtons acting down right here at a distance of 100 millimeters, okay, there's our 100 millimeters, and this is the distance at which it is 90 degrees to that arm, and this force is coming down right through there, so that is 90 degrees right in there. I can say that my moment coming down this way is a moment that is 23 newtons times 100 millimeters equals 2300 Newton millimeters. Sometimes you'll see the milli come in front and people will describe it as millinewton meters. Doesn't really matter, the milli still means 1/1000th. Now, in order to keep this from rotating down this way, this means that out here, I also have to have a 2300 Newton millimeter torque or moment pulling in the other direction. But the difference is out here, I'm at a distance of 300 millimeters. So coming up this way, I am going to have 2300 Newton millimeters equals 300 millimeters times the force of reaction. We can call that point A, B, C, whatever you want to call it. Okay, and to get the answer, 2300 Newton millimeters divided by 300 millimeters, because we got to get 300 off this side, so we just divide both sides, and we bring in the calculator, and 2300 divided by 300 is going to give me 7.66 coming up right here. We'll say 7.67 newtons. So my force acting up this way on this node right here, being supported by the ground, is going to be 7.67 newtons. And because my structure is remaining stable, it's not accelerating up or down, that means that the force being exerted by the ground is similar to the force being exerted by the external load. So I can say that the force at this point right here has to equal 23 newtons minus 7.67 newtons, which is what's acting down here, or 15.33 newtons acting upwards right in here. Okay, so we did that a while back, and this is a skill that I will expect you to have, and this is the first step to solving any of the truss problems that we're going to have, is calculate what forces are acting right in here. And if you're good on that, you're on top of it, that's great. I hope you've just fast forwarded past that part and zip ahead at twice the speed to the part that you're going to need to know. But that's core stuff that I do expect you to understand and pretty much have mastered. Okay, so now we've got these forces acting right in here. And now what we want to say is, well, which is going to be in compression and which one's going to be in tension, and how much force in tension and compression. Well, acting up and down right in here, we need to do a little bit of Pythagoras. And we know that the length of this member right here is going to be the square root of the two sides squared. A squared plus b squared, in this case, a squared and b squared are the same, is going to give us c squared. So we take the square root of that, and that's going to come out to be 141 millimeters. And after you've done a bit of engineering math for a while, you get pretty good at realizing that this is just the same as, square root of 2. You memorize certain numbers. So this is going to be 141 millimeters back and forth in here. And this one is going to be 100 millimeters high plus 200 millimeters. So this is square root of 100 squared plus 200 squared. Is going to be 223 millimeters from right there to right there. Now, those dimensions are really important because just as we've got the dimensions, those give us the similar triangles to tell us how much force is going to be in each of those members. So in this case, I've got 15.33 pushing up on this node right here, and that 15.33 up is going to be the vertical component of the overall stress that's being carried right in here. So this member right here is in compression, and the vertical component of this part of the compression is 15.3. Now, because our dimensions are similar, okay, so we've got 100 going up and 100 coming over, it will also have a horizontal component of 15.3 newtons because these two are the same distance. And if I take 15.3, divide by 100, and multiply by 141, that means that the overall compression in that member is going to be 15.3, 21.57 newtons. I was going to say, could just round that off to 21.6. We do have margins of error approaching 10% right in here. So, yeah, keeping too many decimal places, doesn't really make that much difference. Over on this side, we've got 7.67 acting up in this direction. Okay, so again, this member is pushing up on that one. So we've got a compressive force acting in this member because it's pushing on both nodes. But coming over this way, you'll notice that this vector has to be a little bit longer than this one right here. We've got 7.67 going up in the 100 direction. The 200 millimeter direction is twice as long, so our horizontal component is going to be twice that, which is going to be 15.33, thank goodness, because this force right here and this force right here have to balance out, because right in here, this one is pulling out this way, okay? And so this member right here is pulling in on those two nodes. It's pulling this one in this way with 15.3, and as it pulls that one in at 15.3, it's also pulling that one in at 15.3. So we've got 15.3 newtons in tension in the bottom. And up on this side right here, we've got 7.67 going up, and the distance right here is 223 relative to that 100 dimension, so 7.67 divided by 100 times 223 is going to give us a force of 17 newtons, 17.1 newtons, we'll say, pushing down that way, and 17.1 pushing up that way, but pushing at such an angle so that it's pushing over with 15.3 and up with 7.67, and this one's pushing up with 15.3. You add the 15.3 and the 7.67 together, and you get the 23 newtons. So let's write that out in a nice clear format right down here. There's our 10-pound or 23 Newton force. Keep in mind, that's just one truss. We've broken this down into the two segments of truss. So our overall structure is going to have two members like this. And right here, we've got a 141 millimeter long member. And it's supporting 21.6 newtons. And over here, we've got a 223 long member, and it's supporting 17.1 newtons. And down at the bottom, and we should say those are in compression because that matters. And down at the bottom, we've got 15.3 newtons. in tension, and I'm not worried about the length of the tensile member because that doesn't length doesn't matter for tensile forces. Length matters for your compressive forces. So here we've got all of our forces taking place in here. And the next thing we had to do was figure out how big should I make my compressive members in order to support those forces. So I went back to our original data that I'd gathered um, on the in the testing lab. And let me pull some of that data up. Okay, here I am. And this is where we were gathering data in this lab, and we went through and we tested a number of different samples at a number of different lengths. And this video is up on YouTube, so you can go and take a look at all that. We talked about how they bent. And
We had to
then
do a few
towards the
different
end right
thicknesses,
here,
and it's good to have
we came up with a chart that looks something like this. Now, you'll have different cross sections and you'll have different members, and hopefully you've shared this with at least a few of your fellow students so that you've got more data. But what we were looking for is I was looking for a member that was going to be 141 millimeters long, okay, right over here, that could hold 21.6 newtons in compression. So this video clip right here doesn't have the bottom members, but this was 50 millimeters long at that line, 100, 150. So my 140 line is right in here. I was testing a 3 millimeter by 4 millimeter section. Here's 10, okay. Now keep in mind it's a logarithmic chart, so when I was sketching this in at 150, I was holding 20, and if I sketch that line in right there, 140 suggests that this member right in here, a 3 millimeter by 4 millimeter section, should be capable of holding about 27 newtons in the tests that we did in the lab. So I took a look over here and I said, well, if I need to hold 21.6, then if I make this a 3 millimeter by 4 millimeter member right in here, it should be capable of holding 27 about, and we should be good. Okay, so that was where I said I'm going to make this a 3 millimeter by 4 millimeter member, and it should hold about, based on that chart, 25 to 30. I said 27 newtons. We're loading it at 22 newtons. I should be pretty safe. In fact, I should be able to make it a little bit less than 4 millimeters. But at this point, I thought I'll just leave it at 4 millimeters. I've got the data for that, and um, we'll see where we go from there, because I want to take a look at this side over here. Now, this side was going to be 223 millimeters long. It was going to hold 17.1 newtons in compression. Now, I hadn't been through and done enough testing to have all of my data, but knowing some of the things about beams and column buckling that we've talked about in a previous video, I could make some guesses and estimations, at least to have as a starting point. So what I said was, well, okay, where's my 223? So here's 50, 100, 150, here's 220, here's 250, so 223 is going to be right in the middle. And if I sketch that right through there, you can see the point that I've got the mouse on right now is on the 10 Newton line. So based on that little chart, I'm predicting ballpark a 3 millimeter by 4 millimeter. If I made this one at 3 millimeters by 4 millimeters, it would only hold 10 newtons, and I need it to be able to hold 17 newtons. Now, I could have gone back and tested a 3 millimeter by 5 millimeter section, and a 3 millimeter by 6 millimeter section, and a 3 millimeter by 7 millimeter section. Except there's some theories that we've got and some knowledge that we've got about column buckling. And it's really based on beam bending. And our beam bending has this formula that involves something called, well, we call it the moment of inertia, but it's really technically something called the second moment of area. And to solve for it and to get these formulas, you have to do a little bit of calculus. But once the calculus is done, we can use the numbers without using any calculus. And what it tells us is that the moment of inertia is equal to the base times the height cubed divided by 12 for a rectangle. So what does that mean? Well, the base is always going to be the direction that it's going to buckle. And when we're looking at a beam, we call that the direction of the applied load. So what we're seeing right in here is that we're assuming that the load would be being applied sideways on here, pushing this way. Well, we also know that's the direction it's going to buckle because that's the narrowest member. And in fact, if you think about those videos at the beginning, that column was buckling in the 3 millimeter direction, not in the 7 millimeter direction. 6.7. Where did I get 6.7 from? Well, I said if I know a 3 by 4 has a strength of 10 and I want a strength of 17, oh, rewind backwards. Because I'm talking about column buckling here, I drew it all upright. This is all designed for the force coming down this way. And I've drawn it with H larger than B because that's what you'd do if you could. In our structure, we can't do that because we're limited to 3 millimeters. So our H, we can't change. The H is stuck at 3 millimeters and the B is actually going to be a little bit longer. We're going to be at 4 millimeters. So our rectangle is going to look something like this sort of shape. Um, so anyways, what I need to do is I can't change the H because that's the thickness of the 3 millimeter MDF, and I've set the rules so that you can't use anything else. Ideally, you'd use a thicker piece of MDF to get a stiffer member in there. So what we're going to do is we're going to increase the B, which was at 4 millimeters, to give us 10 newtons. And if I want to make this number 1.7 times bigger to go from 10 newtons up to 1.7 up to 17 newtons, then all I need to do is make that 4 millimeter 1.7 times larger. So I came in here and I said 4 millimeters times 1.7 equals, I think that came out to be 6.8 newtons. Or sorry, 6.8 millimeters. We'll get back to newtons in just a moment. And I said, okay, right in here, I'll cut this out and I'll make this 6.8 millimeters by 3 millimeters. And that should hold 17 newtons because a 3 millimeter by 4 millimeter piece should hold 10 newtons. So if I bump that width up by a factor of 70%, then my overall structure should be 70% stronger. Then we went and we did some tests. And that was what we saw was that we actually got this structure when I did my initial tests. Like I say, I couldn't get it to hold 10 pounds because I was hanging the 10-pound weight off of it. And so it didn't meet these loading criteria. But that was because the weight was swinging back and forth. And so watching carefully what's happening can tell you a little bit about your structure. With our new jig where the weight is applied perfectly vertical and you get a chance to get it perfectly centered right on there, we saw it fail. But we saw it fail at 68 newtons, 6.8 and 6.9 kilos. We retested this after the student came and told me that we had a 6.8 kilogram failure. I'm just like, there's no way this structure should have held 68 newtons. We just did our calculations over here, and this one side should have buckled at 23, which means it should have held 46, or it should have failed at around 4.5. If he'd said it failed at 5 kilos, I would have been quite satisfied. But what was going on, and why was it failing at this higher number? Again, it's good. It exceeded our predictions. So, the Portman Bridge hasn't fallen down here. It's stronger than we expected, but maybe we could make it lighter. Maybe we overbuilt and we could get a structure that would hold our minimum required load without making it, um, without needing to spend so much mass, waste all that MDF, making it strong. So it was time to take a look at our calculations and find out a little bit about what went on. So if we were had this structure and it was supporting, um, well, we'll say 6.8 kilos, that means that each side was supporting 3.4 kilos, or we said we'd have 34 newtons coming down on each side. Let me just grab a new sheet right here. So try and draw it a bit bigger because the window's a bit smaller now. So if I was getting 34 newtons coming down on an individual side, then I'd have more force coming up right in here, and I could go back and redo those calculations. Actually, if we say it's 33 newtons, those calculations get really easy because this is 1/3 of the mass because it's 3 times the distance that it's located at. So we'd have 11 newtons out here, 22 newtons right in here. This member right in here was actually supporting, again, this is 1.41 times as long as this is right here, so we can start calculating this a bit more quickly. This was supporting 31 newtons, and out here, this was 11, 2.23 times as long right here as it was right there, 24.5 newtons. So this was actually pretty close. We said that this side should be able to hold at least 27 newtons, and it was, the most we were able to load it up to before this side buckled was 31 newtons. But over here, this was supporting 24.5 when we thought it should have only supported 17 based on our theory. And that's where these tests came in. And observing how it failed was so important. Just make sure that pops up there. And here you can see this one mode of failure comes down kind of in that S shape. And over here, you can see that this mode of failure comes down are we right? Ooh, right there. You can see it's straight right here, and it's not behaving like our structure was when we were taking a look at, where are we on here? In this video right here, it's not behaving like we saw when we tested these samples, and they buckled out to the side this way. These ones are pinned at the end, but the other ones, in reality, when we were testing it, you can see are fixed and parallel at the end because of the glue around the node. Now that makes them a little bit stronger. So I went back and said, this is great because the lecture we were supposed to take a look at today involved the Beams and Columns 2 handout that is available for you to download on Desire to Learn. And here you can see a diagram that I've copied straight out of an engineering textbook. And the engineering textbooks do talk about the importance of the loading conditions and how the ends are put together. And so here you can see pinned at both ends. This is what we were doing in our compression testing lab, and you can see the shape where that bends out, just like in that what we were looking at. But here you can see where they're fixed at both ends, and there has to be a 90-degree joint right in here. So that's kind of like if you buried this end in here. So if you drilled a hole into your loading platform and your loading platform was perfectly rigid and it was just coming straight down, this part can't bend or flex in there. That shortens the overall flexing distance. And if you look at the buckling load formula on here, it goes from pi squared EI over L squared to 4 pi squared EI over L squared. So since pi squared EI over L squared is the same in both equations, you can forget about all the fancy stuff in here and you can just say, wow, this one is 4 times as strong. Over here, you can see, well, if it's pinned at one end and flexible at the other, it's going to be about twice as strong. But if you're only, you know, braced at one end, this would be like taking a pole and planting it into the ground. So a big piling or something, you're making a fence post, maybe a tree, the amount of force that it could hold up at this end would actually be 1/4 what it would be as if it was pinned at both ends right here, because here it's free to flex back and forth from side to side as well as bend. And condition here where it's planted at the end but has a roller on the top. All sorts of unusual different loading conditions um, that you might be facing. In fact, this is starting to get a little bit closer to what we're looking at in our condition, because here you can see it's square at the end, but it's free to flex to the side. And when we take a look at what's going on in our videos, right here, that's exactly what we see. It's popping out to the side this way, but secure at that end, but it's also um, down here, able to have a little bit of flex. So things start getting complex in here. So if we do our planning using the basic data that you've got for the pinned end, the data that you gathered from your lab, your structure is going to come out stronger than you expect. How much stronger gets a little bit interesting to calculate because you've got an interaction between all the different nodes and all the members in there. And this is where things start to get really cool. Again, you can go through and you can do all your calculations and figure out, how big you need to make each member using your data, and your structure should be able to handle that. But if you want the most precise data, what you need to do is, and you've seen these designs develop before. Let me just turn off one of those cameras so you can see this a little bit better. And this is in a program called Fusion 360. And this is what we've call finite element analysis. And this is a particular type of analysis known as a buckling analysis. And in finite element analysis, you've seen these pretty pictures before. And what's been done is, let me turn on the mesh right here. And you can see that the entire structure has been broken down into a triangulated mesh. Here's our load being applied right up here. I've applied a load right on it. And I've put a constraint down at the bottom right here. And let me drag that back onto the screen. We've got a constraint right down here as well. So we've got our load conditions set up exactly the way that we expect. And here you can see it simulated the buckling that we expect to see. And down here, it tells me that I just applied a 1 Newton load to it, and it tells me that it will finally buckle at 65 times that load. What we observed in the lab was that it buckled at 68 and 69 newtons. This was predicting a 65 Newton failure. That's accurate to within a few percent of what we actually saw, and just a hair conservative. It's a beautiful engineering calculation. Now, when I was a student at BCIT, doing a calculation like this was probably PhD level work. Okay, at that time, simply developing the mesh and getting a meaningful mesh was a lot of work. Setting in the load conditions and all that, and then interpreting the results was really, really hard, difficult to do. Now, Fusion 360 will take your CAD drawing and in the course of 10 minutes, give you an answer on how strong your truss will actually be. I'll show you how to do that in a separate video. In fact, I already have a video up on YouTube that shows you how to do this. And my video using Fusion 360 to simulate a truss has been up there for a while, and it's been used by a number of people to go through and simulate the truss with the previous loading conditions that we were working on for this project. And I actually go through and show you how to set the truss up parametrically. So if you want to change the geometry on here, you can go through, and the beautiful thing about Fusion 360 is that each of these members right in here um, has a dimension applied to it. And when you change the dimension, it changes the overall structure. So this is a little bit more complex of a design, but it goes through and shows you how to do your analysis and then come back and modify it to make your truss stronger. I'm not going to dig into that video right now. It's up there. If you're looking for the ultimate way to design and analyze your truss, it's waiting for you. I will give you another video that shows you how you can take your design off of AutoCAD, so using skills that you already have, pop it into Fusion 360, and get really accurate predictions on how strong your truss is going to be and where it's going to fail. So at the beginning, I was saying, well, what really matters? Okay. What sort of questions would I ask? What do I expect you to know coming away from this? And I want to go back and summarize that because I think you actually know more of what I'm getting at than you think you do. I'm adding extra content in here and showing you big fancy structures. And really what I'm getting with that is try some small samples, look at them carefully, watch how they fail, and then let's use some of the technical terminology to discuss how they fail and use that to make a nicer design. Okay, use the high-speed video cameras and that are built into phones right now, and get a good shot of your structure when you do your small scale test to see how it breaks. That will inform you on how to build your larger structure. And as we sort of go through an iterative design process, some of these concepts will start to become more apparent. Okay, it's a little bit difficult to see right now because we're looking forward, and when you look forward, everything diverges like that. But when you get to the end of the project and you look back on your structure, it'll be a lot easier to understand because everything will go back and you'll find that each of these little pieces has a place in the overall context of what we're doing. So let me just go back and recap some of the key things that we need to know so that you've got the concepts that we want to talk about as we move forward. Okay, so key concepts as we move forward. Well, truss analysis. Okay, we start with a truss. I give you some dimensions for the truss and a load. You can calculate the reaction forces and the compressive and tensile forces in each member. And hopefully you look at a truss and you quickly say, what's in compression, what's in tension. Why does it matter what's in compression and what's in tension? Well, it matters because the part that's in tension can be really thin and light. You can use a rope or a string, or in our case, a little 1 millimeter wide piece of MDF in there to support that. It doesn't have to be strong at all. Well, it has to be strong enough to support the load, but you don't have to worry about buckling when it's in tension. Buckling loads really matter, okay? Now, buckling loads really matter because they are compressive loads. And things, when you compress them, pop out to the side. Take a ruler, press on the end, pop out to the side. Now, it always pops out in the skinniest direction, okay? And it can do a couple of different modes of failure. It can do a mode of failure like this. So if it's pinned at each end, it'll go into a nice C shape. If it's fixed at both ends, you can see how it kind of goes straight and then it buckles out. Sometimes you'll also get it so that it buckles out. Where's that camera gone? In an S shape like this. So you got a couple of different ways that it can fail with fixed ends in there. But just take a flexible piece of plastic or something like that and just play with it. You'll see how that buckles and how it fails. And we've got formulas that can explain that. Now, you don't have to go through and calculate all the formulas from scratch, but what you should be able to do is know that, and here, let's put this down, okay, when you double the length. A column strength decreases by a factor of 4. This is because in our overall buckling strength formula, which is pi EI over L squared, okay, the length is what we call the strength is proportional to the inverse square. So if I increase the length by a factor of 2, my strength is 1 over 2 squared. If I increase the length by a factor of 3, 1 over 3 squared, my strength of the column would be 1/9. If I shorten the column and make it half as long, 1 over 0.5 squared is going to come out to be a factor of 4. So if you make the column half as long, it becomes 4 times as strong. So short members are a lot better for columns when loaded in compression than long members. As soon as you start to get long members, you need to start making them much heavier in order to handle the load because their strength goes down by a factor of L squared. All the other big formulas, you can let those go off to the side. Columns get weaker really fast as they get longer because the strength goes down with the square of the length going up. Okay, so that's one thing that we need to know about columns. The next thing that you need to know about columns is that to resist that buckling, okay, you've got a formula for the moment of inertia, okay? Now, for a rectangle, that formula is BH cubed over 12, where H in column buckling is the smallest dimension. Now, in beam bending, it's not the smallest dimension all the time. It could be the smallest dimension depending on how you've set it up. But we always know that if you've got a structure like this, that it's going to buckle by popping out to the side. It's not going to flex that way because it's a lot stronger in this direction than it is in that direction, just because you've got more material here. It's going to pop out to the side. So our H in this case is going to be this direction right here. Okay, and our B is going to be in that direction right there. So if you can increase the smallest dimension, okay, of your structure, then you get a benefit of H cubed. But if you can only increase the big dimension, then you only get a linear B to the 1. You know, double this and your column is twice as strong. Double this and your column is 8 times as strong. Now, we're pretty much limited on here. For a lot of these members, we're going to have H being 3 millimeters because we can't make it any bigger than 3 millimeters thick. If you've got some very lightweight members in there, you might get some where you can actually cut them down so that they're less than 3 millimeters. In that case, you have control over H. But as soon as you get above 3 millimeters, the thickness of the wood says your smallest dimension is going to be 3 millimeters, and the only thing you can do is you can make it thicker. So, or wider, I should say. If you need to make it wider, just take a look at the strength that you predict you're going to need, and then take a look at the strength that you've measured, that you've got calculated, and it's just a linear ratio. You need something twice as strong, double the width. Okay, that's about all there is. When you're looking at columns, the strength goes down with a square of length. You make something 1.5 times as stronger, it's 1.5 squared times weaker. If you need to counteract that, then what you need to do is you need to adjust either B or H. Ideally, you want to adjust the smallest dimension because that's a factor of cubed, but in our specific loading conditions for this specific challenge, you're limited to a 3 millimeter thick piece of MDF, of hardboard, so you can't change to make this number any bigger than 3 millimeters. So quite often, you're going to have to settle for changing B, and B is just a linear factor. If you need it twice as strong, make B twice as wide. You've got data that you obtained doing your compression tests that will give you some baseline figures, but you can expect the results to come out stronger. That's all you need to know. If you want to do more accurate testing and simulation, there's something called finite element analysis, which we can access through Fusion 360, which AutoCAD gives us for free. Okay, well, for free. Very nice marketing by AutoCAD. Get all the teachers and all the students to use your products. And then when they go out and they're working in industry, they'll say, oh, I can solve that problem if you buy me a commercial copy of Fusion 360. And Autodesk makes a sale. Really, we're the advertising shills for Autodesk. So hi, Autodesk, I'm doing you a favor now. I'm forcing my students to come and use your cool and awesome products so that they think they're cool and awesome too. I will post another video and I will show you how to take your drawing that you've drawn in AutoCAD, and I'll go over how to make that drawing in AutoCAD and then take it into Fusion 360. You just have to download Fusion 360 and you can get beautiful, colorful charts on how to calculate your truss. All right, folks, there we go. I hope that's gone back and covered some of the basics for you. Yes, it looks a little bit blurry going forward. Stick with it. We're not done yet. We don't have a lot more new content to do. What we're going to do is we're going to spend some time chewing over the content that you've got already and applying it and bringing it back to make it all work. Hang in there.